is devoted to the rest of the slide is devoted to explaining qualitatively Marcus theory, which is the way that we think about the rate constant for photoinduced electron transfer in these systems, where kind of uniquely, this is describing the rate constant for photoinduced electron transfer. There's some electronic coupling terms inside of this prefactor, but the key prediction here is that you've got your Gibbs energy change for the reaction, you've got a reorganization energy associated with the reaction, and only when those two things are equal do you get the maximum rate constant for that process. If you're too low, the rate constant gets small, but also very counterintuitively, if you make that driving force, that Gibbs energy change too large, then the rate constant starts to decline. And the reason for that inverted regime is that when you start driving this energy of your charge transfer state too low, you start to build in this activation energy, which is not present when you're at the optimal driving force. Okay, so here's just an example of how profoundly these kind of dielectric effects can change the photophysical outcomes. This is a classic example, I would say, of solution phase photoinduced electron transfer research, where this molecule is designed to produce a long-lived charge-separated state. And broadly, these things are known as donor bridge acceptors. So you've got, although in this case, it's sort of a mixture of what's donor and what's bridge and what's acceptor. The way that this works fundamentally is that you photoexcite this porphyrin unit, you get electron transfer to the fullerene, and then the whole subsequently hops over to this carotene unit. So you get this pretty large charge separation distance. But what ultimately happens in solution depends strongly on what the solvent dielectric constant is. And so this is just a plot from their paper showing the yield of triplet states as a function of solvent dielectric constant. So as the dielectric constant gets large, what's happening is you're changing the energy of the charge transfer state. And when that energy is high, it can relax directly back to the triplet state on this carotene. And essentially, that's what happens on a pretty fast time scale. Charge separates, it goes straight back to the triplet state, and that's what you wind up with. But as you drag the energy of the charge transfer state lower and lower by increasing the dielectric constant in the environment, you start to bring the charge transfer state energy below that of the triplet state. And so now the only recombination pathway is for the charge separated state to go directly back to the ground state instead of through the triplet state. Another example of this that quite surprised us is one that we stumbled across recently in our BioLite project, where the student was, studying this ion pair of this iridium chromophore with this BARF anion. And we wanted to do our time resolved dielectric velocity measurement on it, which meant he had to put it into a low dielectric constant solvent. And when he did that, he basically all his solutions started turning red just under glove box light, when this is normally a nice pale yellow. And he kind of went to the BioLite team and it's like, hey, I think that when I photoexcite this iridium complex, it's actually oxidizing my BARF anion, and it's just falling apart. And everyone kind of laughed at him, because if you look at this equation, neglecting these two terms, what you find is that the driving force at high dielectric constants that I'm plotting here is, it's positive 150 MeV. But it turns out that when you include these terms and the fact that oxidizing the BARF takes you from an ion pair to two neutral species, it actually means that as you decrease the dielectric constant along this axis, the Gibbs energy change for that reaction actually becomes quite negative as you get into these low dielectric constant solvents. And so these data points are the measured rate of the transformation from the nice, sort of yellow starting material to the red final product as a function of the solvent dielectric constant. And then here's just the calculation of what that means for the Gibbs energy change. Okay, and I'm not going to get into this in detail, but I also have my own somewhat idiosyncratic view of how free charges separate in organic photovoltaic systems, these solid state, low dielectric constant materials. And that also has dielectric constant explicitly in the formulation, determining essentially how far away from the positive charge center these electrons have to get before they can become free in the system. So there's all kinds of reasons we think that should matter. But after all that, the first data I'm going to talk about is sort of pushing dielectric constant to a side and just looking at what the excited state dynamics are in the N2200. And the reason that I got particularly curious about this is that the most detailed photophysical characterization I could find of N2200, given in this paper from 2021, showed that the excited state dynamics really don't change much between solution and thin film, which is pretty weird for organic semiconductors. But on the other hand, N2200 is known to aggregate quite substantially in solution. I don't think you can make a truly molecularly dispersed solution of N2200. At least I haven't been able to, or convincingly been able to. So then the question is, right, are these kinetics the same because of some intrinsic property of this backbone structure, or are they the same because you have aggregates in solution, and so photophysically the chain in solution is undergoing significant concentration quenching, perhaps producing exomers or something like that. So Seth's group was able to make these very nice model compounds, giving you the essentially donor acceptor donor structure and the acceptor donor acceptor structures, so that we could start getting at this question, where these we can dissolve directly in solution, and because of their molecular nature, you're going to get sharper spectra. It's just going to be, I think, easier to figure out what's happening in these model systems, and then we can compare it to N2200 and see how that works. And I got to say, my hypothesis going into this was that you were going to make these things and they were going to be a lot more emissive, probably have significantly longer lifetimes, commensurate with many other donor acceptor sort of intramolecular charge transfer state molecules, where often you can get quite substantial emission from those ICT states. But the first simplest experiment showed that that's not the case. So this is absorption on the left axis, and these solid traces, and emission on the right axis with these dash traces, showing that for N2200 in solution, dilute solution, as well as the ADA and the DAD compounds. And the emission of these things isn't any stronger than what you see in the N2200, though there is a distinct difference between the two. So the ADA seems to have somewhat higher PL quantum yield than the DAD, but it's very low in both cases. Additionally, you can see from the absorption spectra and comparisons with thin films of this DAD compound, which I don't have on this slide, that indeed you do have isolated molecules in solution. You don't see the redshifting in it. Characteristic redshifting that would indicate aggregation of these molecules in solution. You go and look at the TRPL, and the story is pretty similar. So these look different, but that's because it was different instrument response functions, measuring N2200 in solution versus the ADA compound in solution. But if you fit through that instrument response function, the time constants you get out for the PL lifetime in these two cases is basically the same, right? You've got two components. The dominant one is 25-ish picoseconds in both cases, and then the longer one, 125 picoseconds. So, on net, the N2200 is just slightly longer lived than the ADA solution. We can also do that comparison with the N2200 and the ADA and DAD, this time using transient absorption spectroscopy. So here is data from experiments that Melissa and Abhishek and Aruda did, and also Andrew, I think, looking at both the bleach recovery and the decay of the excited state absorption in the solution phase N2200 at several different wavelengths. And what you see is that everything is going back to the ground state within about 100 picoseconds. You do the same thing with the ADA and the DAD, where here I'm looking at excited state absorption. And the same thing is happening, within about 100 picoseconds, everything is just returning to the ground state. Though consistent with the difference in apparent PL quantum yield between the ADA and the DAD, the ADA has a slightly longer lifetime than the DAD does. If you look at the transient spectra of the N2200, the spectrum that you get depends on your excitation wavelength. So here we're comparing 400 nanometer excitation that gives you the local exciton versus 700 nanometer excitation, which is directly into the ICT band. The spectra are different, but in neither case do you see really substantial spectral evolution happening, This purple trace is the initial data at 200 femtoseconds, basically right after the laser pulse, and then you're decaying, and maybe there's some slight shifts, but for the most part, it doesn't seem like much is happening other than direct decay of the system to the ground state. When you look at the ADA and the DAD compounds, you can excite into their ICT states around 525 nanometers. And in this case, although the relaxation to the ground state on net is basically the same rate, you do see pretty significant shifts in the excited state absorption spectra. So in this case, the bleach of the ICT transition is right here for both of them. But there's a significant red shift in the case of the ADA after photoexcitation as it's relaxing, versus this blue shift that you get with the DAD. And I should point out that these data I'm showing here only go out to the first 5 picoseconds, whereas the prior data I was showing with the N2200 is the whole time scale from 200 femtoseconds to 5 nanoseconds. So to help try interpreting that data, we also measured these spectroelectrochemistry data, where here what I'm showing is the spectrum that's recorded on our array detector as a function of time, and in time we're scanning the potential. So what you can see here is the distinct absorption spectra or different spectra that you get as you scan through the first reduction, the second reduction, back to the first reduction, back to neutral, back to the first reduction, etc. And I don't know how everyone else in the center is recording this kind of data, whether you just go to one potential and record a spectrum, or if you do something more like this, where you record a spectrum at every potential. But I think it's worth, this is kind of a side note, I think it's worth discussing as a center how we want to do this, because exactly what spectra that you get depends pretty strongly on where exactly you look at it. The spectrum I picked here that's nominally for the first reduction is going to be somewhat different from if I were to take a similar slice right here or right here. Because although it looks like everything sort of is nicely reversible in this image, when you look at it in detail, it turns out not to be. The other thing you can do with this is, you can take a slice in the opposite direction and get something that looks like well, I don't know if there's an established thing to call this a cyclic absorbogram. So you can watch how a specific absorption peak changes as a function of potential, which can isolate specific components of the redox process. Where here what you see is this change in absorption specifically associated with these two peaks in the CV curve, right? So blue is the CV that was recorded simultaneously with this, and red is the change in absorbance as you scan through those different potentials. All right, so the reason that we did that was to take those slices, try to look at the first reduction and compare it with the TA data to see if we can correlate what we're seeing there with the anion spectrum, right? Because when you excite this ICT transition, at least nominally, in the very simplest picture, right, you've got a hole sitting on your thiophene unit and an electron sitting on one of your NDI units. And so comparing the anion spectrum that you get through spectroelectrochemistry with the TA data can be a fruitful way of figuring out if that how accurate that simple picture is, basically. Right, so here's the red trace is the difference absorbance spectra for that first anion. The blue is the corresponding absorbance of the neutral species. Same is shown here for the DAD compound. And when you compare this with the TA spectra, which have been scaled to give you at least roughly the same wavelength range, they don't match that well. Like there's some correspondence, but it doesn't seem to be anything like as simple as integer charge transfer between the donor and the acceptor units. You see the bleach in both cases, which corresponds well with where the ICT absorption band is. And one correspondence is that when you either photoexcite or reduce the DAD, you get a deeper, stronger bleach than when you do the same thing to the ADA. And I think this makes sense if you think of these NDI units as being quite electronically decoupled from each other, right? Here, you reduce one of them, and it only partially bleaches this ICT transition, because you still have an ICT transition between this still neutral donor species and the neutral acceptor species. Whereas in the DAD case, when you reduce the NDI in this case, you do fully bleach the transition, and it's much, much stronger relative to the ADA case. And that bears out, right? The same thing happens in the TA spectra of these two compounds. But when you look at the excited state absorption, there's some correspondence, right? Like you got like a bit of a peak here in both cases, but it's certainly not an exact match in spectra. Yeah, so and then this is just comparisons. Like you do get different results depending on whether you excite into the ICT band at 525 versus into the local exciton band at 400 nanometers. The spectra look quite different. In the case of the DAD compound, they're more similar, and by the end of the time scale, the 400 nanometer excitation winds up giving you a much more similar spectrum to 525, whereas with the ADA, it never really winds up looking the same.
Obadiah, I have maybe I'm confused with what you said, but what I thought you said is that the bleach in the ADA compound is not as strong because when you excite into the ICT band, you still have an naphthalene diimide, correct?
I see where you're going with that. Yeah, so you're right. I think what I said makes sense with respect to the spectroelectrochemistry, but maybe doesn't make sense with respect to explaining the TA. Because you would still have a neutral.
Go on. You have a neutral. You have a neutral NDI, but you don't have a neutral bithiophene.
Right.
So so what you have is if what you're saying is correct, you have a cationic bithiaphene and an acceptor. So where would the ICT come in? What in your mind would be the ICT that remains?
Well, I think what you just identified is just a mistake that I made.
Okay.
I think that makes sense. I think that logic makes sense in the context of the SEC spectra, because there you would still have a neutral bithiaphene and a neutral NDI left after you've reduced one NDI unit.
Mm-hmm.
But I agree with what you're saying, that that's a flaw in explaining. And maybe it just means it's wrong in this case too, because you see
I
a
think
similar thing happening.
the only thing that I would say is that we still don't really have a good sense for what the excited state absorbances would actually be in these model compounds, both for something that has a photoinduced charge transfer state and something that has either been reduced or oxidized. I think in our discussions last week, we suggested that both the cation and the anion on these systems have absorbances that span throughout the visible. So knowing exactly what the excited state absorbance should look like in the photoexcited molecules is a little tenuous in my mind.
Mm-hmm. I agree.
Can I follow up on that just so I'm making sure I'm understanding? So you're comparing a spectral electrochemistry measurement where you would create a radical anion species. So you put an electron into the effective LUMO of the small molecule and created a new state, versus you take the neutral molecule and hit it with a laser pulse and watch the exciton relax back down in the transient absorption. Is that right?
Yeah, that's right.
Okay. And then the question, and where to Andrew's point is what is it transitioning through, and does it actually, I guess my question is does it ever actually end up as the radical anion that you're alluding to the spec echem? And how would it, where would that hole go?
Right. Yeah, I mean, it is sort of trying to test this ultimately simplistic picture that the excited state could be characterized as bithiaphene plus and NDI minus.
Okay.
And yeah, go ahead.
What I do think is true is that if you do reduce one of the naphthalene diamides, probably some charge leaks onto the bithiaphene, and that it could be that the effective HOMO of the bithiaphene actually goes up a bit when you reduce the NDI electrochemically, and that might shift at least a bit in the ADA compound, the energy of the remaining CT transition, possibly to lower energy.
Yeah. Yeah, I think right now my main conclusion from this is that the excited state is probably, yeah, significantly mixed, right? It's not as simple as just donor plus acceptor minus.
Yep.
Can I follow up with the question here? I
Yeah.
think these type of experiment that compare, excited state spectrum with spectrum reduced and oxidized species are very useful. They provide some qualitative, I say, sense of where things are. But of course, they should never be taken quantitatively, right? So this is where a center like this will have high power theoreticians. So for theoreticians, can this actually be computed with some confidence?
Yeah,
That's a question
we computed this
Yeah.
already.
Go ahead, Slava.
You said they computed it already.
Oh, okay. I did not quite follow. Yeah, we have reached out and been meeting with Slava to try to figure out if what insight can be gained from the theory and what exactly is happening here.
Light ice, and then what's a special request?
Oh, the lemon, yeah, just light ice.
Oh, okay, so just light ice and then it.
Is that I think that's background
Want
noise.
lemonade with it too.
Okay, so from this component of the work, we have some simple takeaways. The model compounds have even shorter lifetimes than the N2200. And so we can conclude that this short lifetime is an intrinsic property of this excited state in this backbone structure and not due to some kind of concentration quenching or external formation effects in the excited state. You have aggregated polymers or thin films. I'm tempted to conclude that the nature of that relaxation just has to do with essentially structural fluctuations in the molecule that lead to those changes in the excited state spectra and mediate fast recombination back to the ground state. And that perhaps the only reason we don't see them in the N2200 polymer is that it's just a broader spectrum with a lot of inhomogeneous variations that mask any such variations. It might also be that the fact that it's a polymer somewhat suppresses those vibrations, and that's why the lifetime is slightly longer in the N2200. But those are conclusions that I would like to see, tested / substantiated by the theory contributions, which are still TBD in terms of their direct comparison with the experimental results. And then the goal for this work is that we get it written up in the next week or two, and then get it submitted for publication in the next month or so. Okay, so on to the thin film work, looking at introducing water, in the simplest experiments. Let's just take the neat polymer that we've chosen, put it in water, do some of these photophysical characterizations, and see what happens. And so the first thing that we went and did was to compare the microwave conductivity and the time resolved photoluminescence in these systems. So we took N2200, we immersed it in water, and in this case, we did what I refer to as an ex situ experiment, where you soak it in water, and then you take it out, and in a saturated humidity environment, do these measurements. And the reason for that is primarily focuses on the microwave experiment, where you're all familiar with what happens when you put a cup of water in the microwave. It heats up, and so that's a challenge we have doing these photoconductivity measurements. But somewhat to my surprise, when we did this, the photoconductivity actually more or less doubled in the neat N2200 polymer, although the lifetime components in these transients really didn't change. And I'm missing a trace here in the TRPL comparison, but basically, consistent with prior results, the TRPL didn't really change, right? Like the solution is barely distinguishable from the thin film, and the thin film is not distinguishable, depending on whether it's wet or dry. When you go and do the TA spectra, TA spectral measurements on these dry versus wet, or maybe I should say damp, thin films, you see something similar, which is that on the face of it, not much seems to change. The spectra, there may be a slight blue shift in the excited state absorption of the N2200 in the presence of water. Otherwise, things look pretty similar. However, what you do notice is that in the presence of water, this the bleach seems to be longer lived. And if you look carefully, you'll notice that the rate at which this excited state absorption is decaying in the presence of water is quite a lot faster than it is in the dry case. And so those two observations are summarized with these kinetic plots, where on the left, I'm showing the kinetics of the bleach of the N2200, and on the right, it's the kinetics of that excited state absorption. And this summarizes the last thing I said on that slide, where there's quite a profound difference in the excited state kinetics, where the dry film, yes, relaxes toward the ground state on this sort of 100 picosecond time scale. But when you get it wet, the fast part of this decay changes by an order of magnitude. So you go from, kind of this tens of picoseconds decay in this region to something that's sub-picosecond in its primary component. But consistent with the microwave data, if looking at this residual bleach, what you find is that the wet film has significantly more residual bleach than the dry film does. You don't see that in the excited state absorption, which we infer to mean that, right, this residual bleach is the charges that we observed in the microwave experiment. But in this spectral window, we don't see their excited state absorption directly. So that's kind of where this component of the project stands. Like I said, it's merging with looking at donor acceptor systems, which I'll talk about a bit in the next slide or two. Conclusions are simple so far, right? You soak N2200 in water, it doubles its photoconductivity, you get longer, sort of long-lived components of the bleach, but it also dramatically accelerates the initial excited state decay. And so I think here is where understanding whether these changes are an electronic effect or dielectric effect due to water penetration, or if it's something to do with changes in the structure or some other extrinsic component of the system, like potentially oxygen that was introduced in the water, is going to be really important to understand in order to figure this out. All right, and so then we come to thinking about these blend systems, where we're still at the stage of take these systems, put them in water, and find out what happens before trying to get into the really detailed questions of what exactly is the dielectric constant, how much water is going in, etc. And so, right, this is just the baseline TA characterization of the donor acceptor blends that we received from Aaron's group, where this is the TA on the dry films, where the donor is PTB7TH, the acceptor is N2200. Right, as you expect, the kinetics of the blend are really different from either the donor or the acceptor, where you go from essentially complete ground state or nearly complete ground state recovery in the donor within the 4 nanosecond time window, and totally complete ground state recovery in the acceptor, to a system which produces a substantial fraction of charges, which lead to this long-lived component that has a pretty different spectrum from the excited states of either the donor or the acceptor, right? So spectral confirmation that the charge transfer is working. We went and did the same thing with the microwave conductivity experiments on the dry film, where here you've got the photoconductivity in red as a function of excitation fluence for the donor acceptor blend, the neat donor, and the neat acceptor. Right? Photoexciting N2200 gives you very low photoconductivity, should point out. And then what we started doing was trying to take these films and immerse them both in water and in a 0.1 molar sulfuric acid sodium sulfate solution, because that was the acid electrolyte that Aaron's group used to do the hydrogen evolution measurements. We haven't had a chance to do that in TA yet, but like I said, one of the things that Abhishek and Aniruddha and I have been working on for the last couple of weeks or more, it's hard to keep track, is trying to do this more in situ. Because the initial experiments we did in the same ex situ way I described, where we would take the film, we would put it in the acid solution, and we would, take it out, sort of shake it off, and then put it in a saturated humidity environment to do a microwave measurement. And when we did that, we made this like qualitative observation that, right, here's the neat acceptor, here's the neat donor, here's the blend. And then when we dipped it in the acid solution, we saw this significant increase in the photoconductivity. And we reproduced this multiple times. But what we also reproduced was that this response decayed very quickly. So you got this initial increase in photoconductivity, and then by the time you'd finished measuring it, it would have decayed all the way back to essentially where it started. And so that convinced us that we really needed to start doing these measurements in situ, not ex situ. And tried a variety of configurations. What we've landed on is kind of, in a way, the simplest thing you can imagine, which is, take one of our microconductivity substrates with the thin film on it, put a droplet of your electrolyte or water on that, cover it with a cover slip, put it in our microwave cavity, and do the measurement. That turns out to be pretty finicky, but it does work, which I'm, right now the data I'm showing here has little immediate scientific value, but I'm very pleased with it because I think it's the first time anyone's probably ever managed to measure a microwave photoconductivity transient with water present in the quantity that we have.
Obadiah,
where
in terms, I'm sorry, in terms of the phi muse, do you have a sense of what the increase has to do with the phi with respect to the muse?
So that is a great question. You mean the increase with the acid introduction?
Yeah.
Yeah. And the way that I hope to figure that out, right? We don't know that right now. The way that I hope to figure that out is by performing one of these fluence-dependent experiments. Because it turns out that this curvature that you see, this reduction in this yield mobility product as a function of fluence, is usually controlled by an exciton charge quenching process, where at high fluence, essentially you generate some charges, but then those charges engage in an Auger recombination process with the excitons. And so effectively it's an energy transfer where the exciton can transfer energy to a charge and it kills the exciton. The reason that that's relevant here is that if what changes in your system is the yield, then this low fluence point gets higher, but this also gets steeper because you've got more charges and that exciton charge quenching process becomes more efficient. Whereas if it's just a change in mobility, all that happens is this curve just shifts up or shifts down, depending on what's happened. And so it's my hope that if we can do these in situ measurements successfully and stably, that we can understand whether it's yield or mobility changing based on whether the curvature of this fluence-dependent plot has changed.
Okay. Yeah, that will be nice.
Although we've not managed to do that yet.
Thank you.
Sure. So there's one sort of surprising thing about this microwave conductivity data that you may squint at if you're a spectroscopist, which is that for the higher fluence transients, you start to cross through zero. And this, I think we understand, it's actually caused by a transient change in the dielectric constant of the water, because when you hit it with the laser pulse, its temperature changes ever so slightly, and that change in temperature changes its dielectric constant. And that is honestly the primary thing that makes this experiment difficult, that you have this this known artifact that we discovered when we were doing work in biolec over the prior 4 to 5 years. But here, the photoconductivity from your sample is quite a bit stronger than that artifact. And also the artifact is linear in power, whereas the signal is on this scale superlinear in power as you go down in laser power. So we can get around that, which I'm very pleased about. All right, so this is concluding all the data that I wanted to talk about, right? And this is the overall conclusions for summarized for everything, right? N2200 seems to eat excited states, and that's an intrinsic property of this polymer. So I was kind of hoping that it would turn out the opposite way, and that we could think of perhaps structural modifications that might lead to better sort of optoelectronic performance from N2200, but that's where we are. And I think that this might motivate looking at other acceptor polymers that have just longer excited state lifetime than N2200 when it comes to the photoelectric chemistry experiments. You soak N2200 in water, some pretty profound things happen, but we still don't really understand why, whether it's structural or electronic or due to some other extrinsic factor. And the PTB7 N2200 blends show pretty similar behavior in that when you soak them in this acid electrolyte, you seem to get this increase in photoconductivity. But again, I think understanding why that happens is going to be my main focus in the next several months. So, all right, and goals. I stated this already, but we're trying to submit this N2200 model compound paper by sort of mid-September, where I'm going to keep pushing on doing experiments on these photocathode materials and identify samples that Casey can take for beam time so that we can start to figure out what structural changes there might be, which might also play into the photophysical changes. We've been able to do this in situ TRMC experiment, but we've been having trouble getting conditions just right, such that we can keep our water droplet present, but we don't get condensation in the cavity, which then ruins the measurement. So that's still a work in progress. And I think when I wrote this talk a couple of weeks ago, I was thinking, it'd be nice to think about submitting a paper on the photocathode stuff sooner rather than later. But given the current puzzle over understanding why the water is doing what it's doing, I think that's just a conversation we're going to have about how observational we want to be versus how sort of conclusive from a fundamental perspective we want to be before presenting this to the community. So that's it. Happy to take questions or suggestions.
So just a quick thing in terms of the comment that Seth made earlier. I just asked Slava, and he said he just got the results for the charged trimers, and indeed he finds quite a bit of a coupling between the donor and the acceptor orbitals. So that points to, confirm is consistent with what Seth was proposing, that there is. You cannot just say, "Oh, it's an A minus." The minus leaks into the bitiophene.
Mm-hmm.
Obadiah, do you you guys must have a transient IR set up, I imagine, and would that particularly for the first project, would that provide any additional insight if you were to do that kind of measurement?
Yeah, that's an interesting idea. By transient IR, you mean like actual transient vibrational spectroscopy, not sort of near infrared electronic spectroscopy. I'm assuming.
Yeah, looking at vibrational modes in excited states, see how that change. That might.
We do have a setup, but I think it's become a paperweight. Like people were really disappointed in how we bought a commercial system and people were really disappointed in its sensitivity.
Yeah,
so I'm not sure we have. Yeah, go ahead, Andrew.
Yeah, I was just gonna say we have two. So our kind of workhorse transient absorption system can allow us to do vibrational transient measurements out to 5 nanoseconds or so. We have not used that one a lot at all, but it is functional. We did also buy the Magnitude Instruments Inspire spectrometer. I think that's the right one. And as Obadiah said, we've been pretty disappointed in its sensitivity, despite what the vendor had suggested it was capable of. Seems to work really well for ligands on nanocrystals, but not so well for almost everything else that we've tried.
Okay. No, so we do have the sub-nanosecond transient absorption IR set up, and we use it pretty regularly. If there's anything, if we could contribute to that project, we'll be happy to do some measurement. I'm not sure. I don't have a lot of experience with the sensitivity, but I think for polymer film, this probably should work.
Yeah, I think that would be really interesting, and you probably have the bandwidth to get to those experiments before we could, so that might be a good opportunity to collaborate.
Yeah, we do. Yeah, we are not labor limited as you guys are. So
I think too, it would be helpful. There's some chat going on in the background too about what theory is calculating, is if they can identify particular vibrational features that would guide this, whether it needs to be FTIR or Raman as well.
So typically when we get the reorganization energies, it can be put in terms of which are the vibrations that indeed relate to it. Slava, if you want to say something.
Well, but I think here regarding infrared is more to identify, because the expectation is that the infrared vibration of donor and acceptor, if it's charged, will change. So if you can do infrared, and my understanding is this what you meant for infrared. So I think you even don't have to do transient. You just need to do infrared under the bias, under the, when you put a bias.
Oh yeah, you mean both spectral electrochemistry in IR and transient IR. We're thinking of transient IR because that's a lot easier to do. Spectral electrochemistry, I don't know we have a cell for it, but I think other group might be able to do it. But we definitely will be very intrigued in the transient IR measurement.
We have done transient spectral electrochemistry. I'm not quite sure which order those words are supposed to go in when you do that experiment. So we've certainly done that for molecules bound to oxide surfaces as a function of applied bias. We have not attempted those experiments on any of these systems yet, but it's something that we're hoping to be able to do soon.
Yeah, and Tim, to clarify, are you thinking primarily about transient IR on the polymer films, or were you referring primarily to looking at the solution phase model compounds?
Oh, I think transient IR solution. What solvent is it?
The experiments we've done have all been in dichlorobenzene.
that probably would work. So we could do both. Yeah, we could look at both. Basically, just complement your transient visible measurement, and see whether there's any will help the the interpretation a little bit.
And we have enough of one of them that we could do that. I think the other one is in very short supply. But I think that would probably be adequate if we could compare one of them versus N2200 in solution.
Okay. I think we had N2200, right? So we could just make a film. Maybe we can just exchange that information. We could probably do that pretty quickly, see what we can see.
Yeah, that would be a good place to start for shipping molecules across the country.
Mm-hmm.
Gary.
Yeah, I just want to comment about the wet in quotation marks. Just as a general thing for the center, this is the key difference, isn't it, between the studies that are taking place in this center than what's been done in the past, because we're trying to understand the effect of an electrolyte in the vicinity of charges in the polymer film, and to have kind of it just be wet is a bit vague. And so in addition to Mike being able to do structural measurements on the system, I think we need a better way of controlling and conveying the information of wet to everybody. So for example, if Tim does measurements at Emory, I know the procedure that we did at NREL, but it might not translate as well at Emory, and you end up doing two different experiments on two different samples. So as trivial as that sound, working out how we can quote have wet samples could be a very, very valuable thing for us to work out. Aaron, that's probably more in your camp to help us come up with that, because I know the samples that the TRMC looked at were kind of very carefully wet, but they were like a wet in a humid environment. It's getting a bit wordy.
Damp.
Yeah,
except for the in-situ
then
ones,
of course when you do the spec E chemicals, you're jumping into a completely new regime altogether. And of course, given your opening gambit about the importance of the reducing and oxidizing potential of the system depending on the environment, it's critical. It is very, very important for us to work that out. Over.
All right. I think we are in a good spot. We have more questions than answers, but I have plans flying around in the chat. I have plans flying around in email, so I feel good about this. Any parting words for Obadiah or from anybody else before the last of us jump off? No? Okay. I think Tim and I are going to try and meet hopefully this week. Tim, I just threw an email at you to try and pull some of this together. Obadiah, would you mind sending us your slides?
Not at all. I can put them on the drive.
That would be great. And then I think what we're going to try and do, and I'll talk about this more in a couple weeks, is to try and start organizing some more subgroup meetings between some of these projects that are and collaborations, just to keep things moving forward. So be on the lookout for those and emails from Mike, Jen, myself, etc. And so with that, I think we should all probably jump off, but I will see you all soon.
Thanks.
Bye.